You. Good morning.
Morning, Dr. T.
Oh
Morning,
gosh,
everybody.
I do not know why. I'm actually okay. I'm just like confused because it's so early. Let's see here. Let's see. What am I doing? I know what I'm doing. Sorta.
Hello, Dr. T.
Yeah.
This is Van. I have a question. Um, Yesterday, I forgot my pink pencil and a red lab notebook. Did you see it in the lab?
Oh, okay. Well, I'm sorry that you didn't know the policy on that kind of thing, but if you leave anything in the lab, it's actually ransomed.
Oh,
Do you know what that means?
it,
When something's
It means
ransomed?
Dr. Terrell's teasing you.
Oh, so you'll receive a note, an anonymous note, and a location, and you have to take $50,000 in a backpack, and then you drop it off at the location. They'll give you the cash. But you have to come alone.
okay.
Yeah. Oh, come on! I'm just joking. I don't know where it is. We'll find it. We'll find it. I promise.
Okay. Thank you, Dr. T. No, I think I left it on the bench, on the table where I do the crystal violet
You
things.
left it on the bench or the table where you do
Oh, yeah,
crystal.
on the table. Yeah.
Oh no, no, no. I'm so okay. So my wife criticizes me very heavily. Oops, let me start my video here. Start my video here. Let's see. Oh, that's okay. That's my nose cam. All right. Well, we'll have to work with it. My wife criticizes me terribly, Van. She says that I joke around when I'm teaching. And she does not like that. And it always used to confuse her when she was a student. My wife she was a student here while I was teaching, and um, so you're in good company. But I will tease. I will tease. I will definitely tease.
That's fine. Thank Dr. T. Thank you very much.
Well, you're very welcome. I think. So let's see here. Um, excuse me. Okay. So what do you guys see in here? Screen one. Okay, that works. Okay. So if you guys can see screen one here, I think this is where we are with the notes. I think we got more or less to here or to here. So those of you who've had labs so far, at least the crystal violet lab, will recognize that there's an important component in 155 in just experimental design. You know, basically handling the horrific challenge of C1V1 equals C2V2, right? And nobody can do it. A few of you can do it, but most of you think you can, but you can't. And it's just, there's just some tricks you got to learn, right? You just got to learn some tricks. And it's because the approach is a little bit different when you're just kind of like confronted with the challenge of making a solution of a certain concentration, and then you have the starting materials. You have too many variables. You have all kinds of different pipettes and different weights and everything that you can use. And so you just got to learn to you learn to do it without getting in trouble. Like, for example, you could do a calculation for like one of the examples is to make a 1 micromolar crystal violet solution. That's experiment 0. And the DH10 folks have been doing that, right? And so you say, oh, we'll make 1 micromolar. Well, let's calculate that out. And so you might start with 1 liter at 1 micromolar, and you do the calculations, and it comes out to 0.4 milligrams. And it's like, there's no way you can weigh that small of an amount, right? It's possible. It's possible to do, but it's just, we can't do it, you know? So, and it's hard to do that accurately, right? So you think, oh my gosh, you know, what am I going to do here? And, next thing is, well, you can make 100 liters, right? But, you know, that's not a good approach. You know, nobody wants to make 100 liters of anything, you know? And so you have to plan some dilutions, right? And so you might want to make, you know, instead of 1 micromolar, start out with 100 micromolar, you know, 10 to the minus 4 molar, right? And then that'll get you the amount up that you need to use a little bit. And then you can get the volumes down and the concentrations in an acceptable range, and then you can dilute from there to solve that problem. So so here's an interesting example, right? Let's say that we have a you need to make a 2 microgram per mil standard, right? So this is a calibration standard, right? Oops, I screwed that up, but oh well. Let's just call it a cal standard. Oops. By diluting a 1.086 gram per liter stock standard here. This is called a stock standard here. So you know, the overall idea is you could take 2 mils and dilute it to a liter, right? 2 mils to 1 liter of this to get this, right? This is C1 V1 equals C2 V2, right? And here we're using units of micrograms per mil and volumes of mil. And so in this case, you know, the unit, what we're saying is that the number of micrograms pipetted is the number of micrograms in the solution that you make, right? So here, oh geez, that's pretty small. Sorry about that. When we get larger.
You probably have to enlarge your text box.
I know, it's just like normally you can hit the font up button there. There it goes. Now it's working. So now I'm confused. Where was I? So concentration in micrograms per mil, volume in mils. And this V1, this is a pipette volume. I see. I'll make a text box over here. That might work. C1 is micrograms per milliliter. V1 is a pipette volume in mils. C2 is a concentration in micrograms per mil. And V2 is a vol flask volume in mils. Yeah. So in any case, I mean, this might be a type of calculation you'll make, 1 times 1,000 over 1,000 equals 1, And this is milligrams per mil, grams per liter. Oh, milligrams per gram, mils per liter. No, this is milligrams per mil. So milligrams per mil. There's another sort of a side note here. Milligrams per liter. Oops, come on. mg per liter is equal to parts per million. And micrograms, come on. Per milliliter are also equal to parts per million, right? So one way to remember this is that a milliliter is about a gram. So a milliliter is equal to 1 gram normally, right? So a microgram per gram is a micro of a gram per gram. So that's 1/1,000,000th of a gram to a gram. So that's a part per million. So that's one way to remember that particular unit. And then there's also parts per billion and there's parts per thousand, right? So grams per liter, oops, are parts per thousand. And actually, Harris is calling it TH now. That parts per thousand, because T is also for trillion, right? So there's thousand, million, billion, and trillion. Yay. And then how about micrograms per liter? This would be parts per what? Micrograms per liter would be parts per what? 1,000, million, billion, or trillion?
Is that parts per billion?
Parts per billion. Thank you very much. And nanograms, per liter is equal to parts per. Solomon, help me out here. I think Solomon's on break. He's taking spring break early. So there's million, thousand, million, billion, and
The thing that comes after billion.
what comes after billion? Come on, Casey.
Trillion.
What?
Trillion, I think. Trillions.
Yes, but you have to say it a little bit louder because nobody can hear you.
Trillion.
Trillion. Excellent.
Yeah.
Parts per trillion. And then below that, you just use Z for zillion. Do you know how many a zillion is? A zillion is a lot.
Not sure. Maybe 15-0.
15 zeros? All right.
I don't know.
think
I don't
so.
have enough fingers.
Yeah, I don't have enough fingers to do zillions either. Because it's, wait, here. Oh, no. There we go. I got to get it in myself here. 1,000, million, billion, and then zillion is just a lot. Okay. So, I probably need to change my background too. Let me see if I can, I might be able to use my document camera today though, so I'm sort of excited about that. Let's see if I can. Ah, yes, I will be able to use the document camera. There's my mouse. Yay. Okay. My hand was feeling self-conscious. Can you believe that? So, if you want to take this another step to do to plan a calibration, then you just have to figure out what pipettes and what not to use. I'm not really sure why, but Harris is sticking with these class A pipettes. Maybe he took the time to learn all this stuff, but it's becoming a little bit of an anachronism, right? Because the auto pipetter, the type where you push the button on the end, if you calibrate them, if you know the actual transfer volume, they're just as good. So, normally what I would do is I would say, well, let's do these calculations, right? But let's do this, not 3, but 0.3, not 4, but 0.4, and then 0.6, 0.8, and 0.9, right? Those are all settings you can use on a 1,000 microliter pipette, right? And then you can also just do, so what is the advantage of doing a single 900 microliter transfer over three milliliter transfers?
Less error.
Sorry, Cindy?
So actually, someone said it before I did.
Oh,
Just because of the error, every time you do a transfer, you're going to introduce more error.
yes, exactly right. There's a little bit less accumulation of error there, right? And so, you know, in this case, we'll be delivering less, but we can use a smaller volume, right? We can use a 10-fold smaller volume. You know, instead of diluting to 1 liter, which is ridiculous, you know, we could dilute to 0.1 liters, you know. So this is kind of how you would do that. I'll color code these guys here, right? Oh wait, no, I don't want green because green is one of their choices. How about blue? I'm just going to delete that just to make space. And, you know, whatever, you know, you can acid wash glassware. I don't really think that it matters at the part per million level for most metals. It depends on how precise and accurate you need your answers, right? But I think that at the 1 part per million level, if you just have a normally clean glassware, then you can definitely get to parts per million without any issues. But you know, you can always acid wash if you prefer, you know. So anyhow, okay, so let's do this guy here. Dilution by mass is more accurate than by volume. This is also an important lesson from Chem 155, is that if you have, for example, in our lab, we have a kilogram by 10th gram balance, right? So that will give you, it's, you know, you can weigh 1 kilogram to the 0.1 grams, and that's pretty good. That's 1 part in 10 to the 4th, right? So that's probably a 64-bit, I'm sorry, a 16-bit analog to digital converter there. And you know, we also have 10th milligram to a couple of 100 gram balances. And so that's, you know, it's, you can, the thing about when you weigh solutions to get a mass concentration, for example, like a gram per kilogram here, right? This unit is also defined. This is actually that definition of parts per thousand, right? And you know, and you can also get a microgram per gram, which is parts per million. Right, and this is actually the way to do it. You know, when you say microgram or milligrams per liter, or micrograms per mil, they're really only parts per million if the solution is 1 gram per mil, right? So if we go up here, I'm just going to switch to the previous slide for a moment. So this is this says parts per million here, right? But this is parts per million if the density is about 1, here, let's grams per ml. Right? Because then, you can say if 1 liter is 1 kilogram, right? Then you can say that 1 gram per kilogram is 1 part per thousand, right? So now this, if you use mils here and you use micrograms here, right? Then you're okay, right? Because the actual amount that you're transferring is going to depend on the volume, right? And not the mass. So if you start with mass per unit volume and you stay with mass per unit volume, then you're fine. If you start with mass per unit mass and you stay with mass per unit mass, then you're fine. You do your calibrations and your standards and your samples will give you that same unit back. Now, it's also true that 99% of the time, if you use grams per ml, you can approximate that as, micrograms per ml, for example. You can approximate that as parts per million so long as the density of the solution is 1.00, right? And in Chem 55, when we dealt with water densities, we often, 1.00 is not a bad estimate, but you have to be aware that there can be some small differences, right? So when you report that answer, you can just recall how you did the experiment and report the answer in the same units. So instead of, like in this case, instead of reporting back in part per million, you could report it back in milligrams per liter, right? Is actually a better way to report that value, because that's kind of how it was done. Okay, so let's do this problem here. Dilution by mass is more accurate than dilution by volume. True, because if you take a pipette, it might be say a 10 mil pipette might be good to 0.01 mils, right? Or 0.1 mils. And it's very technique dependent, it depends a little bit on whether on how clean the pipette is, whether it withholds solution on the inside, whether you get the last bit out of the tip or not, and these types of things. So dilution by mass is normally more accurate than dilution by volume, right? Now, there's another reason that that's more accurate, which is the fact that when you go by mass, the balance will tend to tell you the truth, right? If you use a vol pipette or a vol flask, and maybe you miss the meniscus a little bit, there's really nothing you can do about that. That sometimes there is, right? But normally in normal practice, there's little that you might do about that, right? So so you say, what the hell? It's 20 mils, whatever. It's not 20.01. Who cares, right? But if you use a balance, you just record 20.01, right? Because you'll know actually, my 20.0235, 20.0 to, all right, 023, that would be milligrams, and then 5 would be the 10th milligram digits, right? So you'll know a bunch of digits, right? And so you can just record all the digits, and then you can have a very accurate log of the concentrations, whatever the answer is that you get, right? So that's kind of a cool thing about doing things by volume. And that's one reason you can say it's more accurate and more precise generally than dilution by volume, right? So in 0.48 molar HCl, right? So this, I think he uses this intentionally because this is, the density is not really that close to 1. Oops. What happened? Sorry. Okay, so how many micrograms per gram, or parts per million, are in a solution made by mixing 2.14 grams with 243.27 grams? So the answer there is, so I'll just, oops. 2.145 grams divided by 243.27 grams, this is grams for grams, right? And then we can say times 1E6, or times 1 million, right? Micrograms per gram, right? And then this is going to give us, a large number. A very large number. I might even actually calculate it. So (2.145) 243.27 divide 1E6 times. That's going to be 8,000. 817.4, right? Parts per million, right? Let's see if we have the right number of sig figs. We got 1, 2, 3, 4, 1, 2, 3, 4, 5, right? So probably we should leave it there. Or we could subscript that last guy, right? And that's how we would calculate that, So this is going to be micrograms per gram, which is parts per million. And then I'm not going to dip my toe in this one right here right now. It's I'll let you work through these limited glassware problems, right? Let's okay, so I'd like to get through a couple of homework problems, and because there's actually a homework due on it's Monday night, I think. Let me double check that. Is that right?
Yes, that's correct, Dr. T.
Yeah. Okay. So I did want to talk about that a little bit, but so I'll just go forward right now, and I'm going to talk about Beer's law and then spectrophotometry, and then maybe a little bit about fluorescence, and then we'll go through the a couple of the homework problems. And yes, so okay, so Beer's law, right? Normally, Beer's law, the typical deviation from Beer's law is negative, right? And the normal issue is stray light, right? And stray light is light that gets from the source to the detector, but does not go through the sample. Right? So that means that as the sample concentration goes up and up, the light power that gets to the detector reaches this stable finite value equal to the stray light power, right? You have a new minimum and it's not 0. Now you can compensate for it if you can subtract it out. But it's not super trivial to do that, right? So let me ask y'all another thing here. If, for example, you had a type of spectrometer and you had no, and you had a calibration curve, right, where you were confident in your concentrations, and the absorbance rose in a curve like this, in a negative deviating curve, could you use this calibration plot to determine a concentration, say, with an absorbance around here and a predicted concentration around there? Would that still be accurate?
Maybe if we could fit like a polynomial or a logarithm, or if we could find a function to actually fit to that. It's not going to be a straight line, though.
Right, exactly. So someone else weigh in on this too, or maybe Van, do you understand the question?
Yeah, kind of.
Okay, so what I yeah.
When are we gonna do this by?
Yes.
I'm sorry, who's talking? I didn't understand the question. Could you repeat the question?
You say what happens when we have the negative, the curve of the absorbance versus concentration is lying in the negative deviation. What happens?
Yes.
And the way to fix
you're
it.
cheating. Because I had lower up.
I was trying to mute somebody and I missed that last thing you said.
And you say find the solution to fix that one. Is it the right?
Right. Yeah. So the question is how can you still get an accurate concentration, right? And so Cindy was saying you just fit to a curve as opposed to a line, right? And that makes that should work. And that should normally work. Now, is it preferable to have a straight line fit? Normally, yes. If for no better reason that to define the curve, you need additional parameters, right? So to define a straight line, you need a slope and an intercept, right? But to define a curve, you have a slope and intercept, and then maybe a power, you know, or a coefficient for a power of x, right? So there's another parameter, right? And that will contribute to the uncertainty in the answer at the very least, right? So ideally, or better, a better case is if you have a straight line, right? So in this case here, if you have an absorbance up here, and let's say this is an easily measured absorbance. Let's say this is an absorbance of, you know, 1.5 right here. What could you do practically to that specimen such that if you want an absorbance of 0.15 instead of 1.5? What would you do?
Can we make the solution more concentrated a little bit so that the absorbance will move
Oh,
up
I still just left.
because of the curve?
Casey, what's wrong with that? Good morning.
You know it's too early.
I know. Who else wants to? Cindy, do you want to answer that one?
No,
No. Okay. So,
I'm thinking.
so Van suggested that we make the sample more concentrated. Okay.
For a lower absorbance,
Right.
wouldn't you make it more dilute?
So what's easier, making it more dilute or making it more concentrated?
More dilute?
Can you convince Van of that?
You just gotta trust me. I don't even know if it's right.
I think
Yeah,
how
I
are we
know.
going to? I figured how are we going to concentrate it? Unless we like cook it down or something, but then we can't measure.
Right.
Like
Oh,
if I had a works cited, it would just say, just trust me.
I love it.
The world according to Casey.
Right.
okay. Okay, if we make the absorbance lower, so we have to make the concentration lower. We have to
Right.
dilute it more
Right.
because it's according to the law. So it's
Right.
the same relationship.
Right. So what, okay. So if you had this 1.5 absorbance out here and it was in the curved range here, right? And you brought that absorbance down from 1.5 to 0.15 down here, right? There's a chance that that will be more accurate. What are some of the requirements that be a more accurate value down there at 0.15 absorbance?
Is it because of the two lines is merged right there?
Sorry, Van?
Is it because of the two green line merged together at the lower concentration and the absorbance?
Didn't
So that's
quite-
why it's one more accurate.
Did you understand that, Casey?
No, I got a little distracted. Sorry. Can you repeat it?
Okay. I can't quite understand what you're saying there. There's something two line or something.
No, because we have the negative deviation and the positive deviation. It's both come down from at zero. When we have the absorbance lower, so the two line is merged together.
Oh, right. Exactly. Yeah. So let's ignore the positive deviation now. And let's just, and the straight line. And let's just think about just this curved negative deviation line, right? We had an absorbance of 1.3. and we say, well, let's bring this down to 0.13. And if you had a balance and you needed, say, 10 mils or 10 grams for your instrument, how could you do that? So I'll start you out. You could take your balance, put a beaker on the balance, tare it, then add sample until you get to about 1 gram. Then write down that value. Then what? You need to dilute it, right? Dilute it by a factor of 10, right? So you've taken your, you got 0.9873 grams of sample on your balance, right? And you want to dilute that 10-fold. So you're going to add, say this matrix, say it's, say it's just pure water. You'll add pure water until the weight is what? Are we on strike?
Wait, what are we? What? May you repeat the question, though?
Yeah. Yeah. So if your absorbance is 1.3,
Yes.
and you want to dilute it by weight to get
Yes.
an absorbance of 0.13,
Yes.
then how would you do that? And
By
I started,
volume, or
yeah.
by volume, you diluted more volume, or you weighed out less mass from the beginning.
Right. So I'm saying that by mass, let's say you can take this sample that has an absorbance of 1.3, take a beaker, put the beaker on the balance, tare the balance so that it reads 0, then add this 1.3 absorbing sample until you get 0.9873 grams. Then you write that 0.9873 grams in your notebook, right?
Yes.
Then you add water until what?
Until you reach the desired absorbance.
No, you can't.
Until 10 grams?
Right, exactly. Yeah, because you can't really do this in the spectrometer, right?
Yeah.
I mean, it would be kind of cool if you could, but in this case, we have to actually do the dilution on the balance. Does that make sense, Fook?
Dilution on the balance. Yes.
Yeah. So you just got this 0.9 grams, and you just want to add water until it's about 10 grams, right? And let's say you add water until it's 10.1234 grams, right? Then you write down that value, and now you have an accurate dilution of your sample, and you'll get an accurate absorption here, and then you can get an accurate concentration down here.
Yes.
Anyhow, these are just some thoughts for you, right? And how to sort of deal with, the vagaries of calibration.
Yes.
Good? Very good. Okay, so now, if you never ever want to care about accurate absorption measurement again, you can use a spectrophotometric titration, right? And titration, as you're well aware, titrations tend to be volumetric, right? And you add and add and add and add until you get to an end point, and then you stop and you write down the value, right? Or you go past and you backtitrate, things like that. But you keep track of volumes, right? So in a spectrophotometric titration, you monitor the changes in absorbance to tell where a titration endpoint has been reached, right? And here's an example of a spectrophotometric titration that you can do, right? Now, one of the tricks in spectrophotometric titrations is getting an absorbance right in the cuvette. This is very much like Fook was implying earlier that, you know, oh, you can just keep measuring until the absorbance is 1/10 what it was. Well, if you have a probe like this, you could probably do that. Although I'm not exactly sure, like if that would be the way to do it, if you had a curved calibration. So I think in that case, you would definitely want to do the dilution by volume or by mass, right? Not by absorbance. But in this case, what you can do is you can put a probe. I'll try and make this larger. You can put a probe into the solution, right? And we have one of these for the carries, but I stole it and I lost the mirror. Don't tell anyone. I honestly did, but I was using it for Fabry-Perot interference, which is way cooler. But anyway, so you use a probe that has a fiber. The light source is coupled into a fiber here. It goes through 1/2 centimeter of solution, bounces off of a mirror, then comes back and is picked up by a fiber here, and that is carried on to a detector, right? So one of the problems with this type of detection is that getting the light into the fiber and then getting it into this fiber, then bouncing here, and then into this fiber, and then to the detector. There are some light losses at each of those steps, right? So even if you get a perfect blank, you're dealing with less total light. And so that means that if the light intensity is lower, the light signal will be a little bit more noisy, right? So, and in best case scenario, right, if you decrease the light by a factor of 4, you decrease the signal to noise ratio by a factor of 2. And that what another way of saying that is that if you increase the number of photons that you detect by a factor of 4, you decrease the noise in that measurement by a factor of 2. And that's called, that type of noise is called shot noise. And that's the best you can do with light. Unless you're using a very, very, very strange single photon source. And I'm not even sure then. Does that make sense? So, this type of apparatus tends to have fewer photons. So it will have a higher noise level. So you may need to use a stronger light source. For example, if you could use a laser, then everything's completely fine because you can get a ton of photons with a laser. You know, you can get a ton of photons and you'll never be limited, you know, in a situation like this by the number of photons if you have a laser light source, right? Well, never is probably too broad, but you know, you'll probably have plenty of photons, right? So here is a way to put the cuvette right into the solution that you're titrating. you could have like let's say you had a two or a three necked flask, a round bottom flask with 50 mils of solution in it. You could dunk this down into one neck, put a stir bar in there, and then put the burette into the center neck, and then you'd be done, right? Then you can make this type of measurement where you measure the absorbance versus the volume of a titrant, right? And then you could measure the end point of the titration here by volume, right? As opposed to absorbance, right? So, and interestingly, you can get the information from either axis, right? You could either, take the absorbance, the corrected absorbance, subtract out the blank, which would be this value, right? And let's say this is 0.29, right? And subtract out 0.05, you get 0.24. You could get if you knew the extinction coefficient of this dye here, then you could determine the concentration of EDTA, However, it's generally more accurate to use the volumetric endpoint. I don't know why. I think that's because instruments suck. They just aren't as good, right? So, I don't know what else to say. That's kind of a crude way of putting it. I'm sorry, but there's this endpoint here. If you take it off the absorbance axis, you'll get one answer. If you take the answer off the volume added axis, you'll get another answer. And this answer here will generally be more accurate, right? So here the EDTA concentration to 4 sig figs, right? And then you can know the volume to how many sig figs would this be? This endpoint here.
Three.
I would say you would have at least 3, right? 19.8, 19.9, 20.0, right? And I think you might have 3.5, maybe even 4. Let's give me the benefit of the doubt here. I'm trying to teach a class. Just kidding. I think you could probably, let's say you could get between 3 and 4, 3.5 sig figs here, right? Then you know your answer to 3 sig figs. On the other hand, this axis here probably maxes about 3 sig figs. The absorbance, this red to blue transition, the absorbance is max 3 sig figs. Oops. Okay, ignore all. There we go, turn your blue. Okay, so let's see. So, so anyhow, this is how you do that. Now, there are a couple tricks, right? One is, how do you correct the absorbance? It's really better to use a corrected absorbance, because there are distortions to this curve that appear as you're adding volume, right? If you had, say, 20 mils and you added another 20 mils, then the final endpoint absorbance would be half of what you would expect, right? So for a variety of reasons, it's better to use a corrected absorbance there, right? So the corrected absorbance here, if you added 20 mils to 10 mils, right? The corrected absorbance here, like what you can do is, here we go, is you can take, you're trying to correct back to 10 mils, right? So the operative, I think that the operative equation is something like A1C1 equals A2C2, right? Because here's an absorbance, or I'm sorry, A1V1 is equal to A2V2. Because here is A1 and V1, right? So you want to correct back to the original absorbance, and then the total volume is the diluted one here, right? So even though, A1 and C1 are directly proportional, right? So in a way, we could say, we could take something directly proportional to A1 and multiply by V1, and this would conserve the units, and A1 V1 equals A2 V2. It would be like C1 V1 equals C2 V2, right? But so I'll just put this in quotes, and hopefully, maybe next year I'll have some elaborate justification for it or whatever. But right now, I think this is fine, because what's his name? Harris tends to agree with me here, right? Oops. Whoa, don't do that. Hello, Brendan. Go on. Get on out of here. I'm teaching.
I'm trying to take class right now.
You're taking class. Oh, he's in class. Wait, Brandon, you're on the screen, but you're right here? How is that possible? I don't get it. How can he be in class and he's outside my door? He shows me the phone. I don't understand. Okay. Yes, tears are appropriate, Taryn. Tears are definitely appropriate. Okay. So anyway, this is how you could correct the absorbance, And so at each point, you'd have, 29.8, 29.7, all over 10, right? And so, wait, no, you'd have, yeah, and it'll be, at 0 added mils, right? You'll have 10 plus 0, right? And then it'll reach the maximum correction at the maximum volume, right? Another thing is that when you do this value won't fall, right? As you keep adding the titrant, the absorbance won't fall just because you're diluting the system, right? Does that make sense? So let's do this one here. So if we have 8.94 milliliters of titrant plus 5.00 milliliters of analyte, and this gives us an absorbance of 1.05, then what is the corrected absorbance? And the simple answer here is A core is equal to A uncore times 8.94 plus 5.00 over what? $8.94 plus 5 over what? Somebody help me out. This is your contribution to the mental health of the faculty of San Jose State University. Do you wish to make that contribution? Sorry?
Michael's got it in the text.
Oh, sorry.
Or the chat.
Okay, all right. Sorry. I keep always forgetting to, and I don't see it here. I don't know where it, oh, there it is. There it is. Ah, I can't see it anywhere.
He says 5 mils.
5 milliliters. That's right. Thank you. Thank you, Michael. You know, so this is going to be oh, it's 0.105, so it's 0.105, right? 8, oops, enter. 8.94, enter. 5 plus 5 divide, and times, this will give us 0.292. There we go. All righty. So I am going to I'm going to actually postpone the due date on homework 2 because we are not going to get to we're not going to get to photophysics. So I'll probably postpone it till next Friday. All right. I'm going to do that right after class. Yay. And then what I'd like to do right now is, well, actually, I'll probably have time to go over the problems. Yeah, I'll just go over the problems next time. Sorry, this is a little bit ponderous today, but hopefully we learned a little something here and there in the margins, and I look forward to talking to everybody shortly. Are there any questions? Have I forgotten to do anything or say anything? Or
Dr. T, I just wanted to double check with you for the lab. Is it due? It's not due in 2
Oh,
weeks,
the
right?
labs. Right. I'm not exactly sure when the labs should be due, Fook. You know, and I said I was going to talk about crystal violet today. I did not.
Please don't make it due next week. Please.
No. Probably the week after next. It will be the.
Oh, thank God.
Yeah.
Oh, thank you so much.
Yeah, no,
Oh yeah, right now Canvas says it's due like the day after the last group does it.
Oh, I'm sorry
Yeah.
about that. Oh,
Yes, sir. That's why I was asking.
I suck. I'm sorry. You know, I don't really even, with all this sort of oscillating between who's doing what, I'm not exactly sure how to do the due dates. So I should probably, I'm not exactly sure what to do because there's a weird double-edged sword here, because if I just take away the due dates and say, just turn them in after you finish them, then nobody does them until the very end. And then there's a ton of copying, and it's just not good for anybody. So I have to set some hard due dates, but I just don't know exactly when to make them.
It's not at being.
So
No, not.
yeah, I mean, we can probably make them like 2 weeks after you finish the experiment. That might be a good way to think about it, And if I don't, and if you don't get the support you need, then you can say, hey, Dr. T, I didn't get any help on this. What's going on? And then I'll extend it for you. So it'll be the squeaky wheel approach.
Yes. I'm listening, sir.
All righty.
Thank you.
Cool. Okay, so I am going to sign off now, and Diane, we can chat offline. Pretty sure it's in for Diane here, and you are welcome, Van. Everybody's welcome.
Thank
And
you, Doctor.
I'm gonna take a little break, and then we're gonna start lab. Okie doke.
Thank you.
Thank you. Bye,
Professor.
everybody.
Bye.
See, and we're having fun in lab, so thanks, everybody. I don't know why I said that.
Professor.
Ah, yes.
So you got my email yesterday, right? For the
And I'm just working on it right now.
Oh, okay. Yeah, I was wondering if I should do anything today or just.
I'll let you know.
Okay. All right. Thank you.
Cool.
Dr. Terrell, I had a quick question.
Yes.
What lab day am I coming in? Because I still wasn't told what day I'm supposed to come
Oh,
in.
really? You don't have a lab day?
I don't.
Okay, well, let me, so find a place on the lab schedule where you fit, and
I saw Tuesday and Thursdays free. I was scheduled, the class I enrolled for was a Wednesday lab, but I saw it was full. So that's why I emailed saying I could do Tuesday or Thursday.
Okay. All right. So what I would like you to do is to go to Canvas and look at the rotations, the lab rotations Excel spreadsheet.
Yes.
And then let me know where you fit, and then I'll add you in on that day.
Okay, sounds good.
All right. Cool.
Thanks.
All righty. See you, everybody.